So let's use all of the stuff that we've learned on matrix concepts. So one of the applications is for higher order surveys such as least square adjustments, analytical photogrammetry, we would use these mathematical equations or methods. So let's take a look at another idea of using it for intersection of two lines, a bearing intersection. So this kind of goes back to our coordinate geometry. It's also using translation, relation, scaling, and coordinate systems. We might use matrices on. So the first application example that I want to show you is the intersection of two lines. So we're given an x coordinate and a y coordinate of one point and the azimuth of that line. We're also given the x coordinate and a y coordinate and azimuth of a second line. So here's our coordinates, 10,000, 10,000 with an azimuth of 50. So north 50 degrees east. The second one is 20,000, 5,000 with an azimuth of 330 degrees or north 30 degrees west. Okay, so the problem says find the coordinates of the intersection, the x and y intersection of those two lines, where they cross. So we're going to be using basically a bearing intersection with known points. Okay, first we have to express the equation in a standard linear form. So we're going to say a plus, if you look at the equation up here, a plus x of the intersection plus b1, the y intersection equals c. And the reason we're writing it like that, the general form of equation, if you remember, is ax plus by equals c. That's a general form of your linear equation. So each time I write it, I'm going to call it a's and b's. So get a feel for what this means. So a times x of the intersection plus by of the intersection equals C2. So we've got two equations and two unknowns. So we're going to use matrices to solve for those unknowns. But first we're going to have to set up the C, A, and B. That's where we get the values in the matrix itself. So we identify three matrices to be able to do that. We're going to call it matrices A, L, and X. And we're calling it that because this is normally what you'll see in the survey textbooks that we've got out there. And it's also with the matrices program that you'll be using a little bit later on. It uses the same format. So I want you to get a feel for that format. Now, the A matrix is made up of the coefficients A of X and B of Y. And the C is going to be your L factor. Okay, so that's where all these values are starting to come from. Take a look at the notes as I go through these. Okay, so my first A matrix is going to be a 2 by 2 because it's A1, B1, A2, B2. These are in front of the X's and Y values. Now, my L value is going to be my coefficient at the end, my constant at the end. So it's going to be C1, C2. So the first one's a 2 by 2, and the second one's a 2 by 1. Okay. Now the x is my even though I'm saying x intersection, I'm not actually calling this an x value. It's just an unknown value. So you could call it J, G, F, L. I don't care, not L because we already used it. Any letter you want. But what it's saying is it's your x and y components. Now it's very, very, very important that when you're writing this, it's always the first and then the second value. You can't have those flip-flopped, okay? Because then these equations have to be flip-flopped. Or the order, then it has to be B and then A. Just FYI, that's how it goes. B's goes with Y's, A's goes with X's. All right? So what we're going to do is we're going to have to multiply the X times A to get an AX. That's how it's written. So you can see if I said X is my unknown, then X times A and then B times Y. That's how I come up with this equation. And then the second one is Y or x times A2, y times B2. So our equations look exactly like we have this written, looks exactly like that up there, okay? Now, the matrix A and L are as this. So we have to come up with the constants. So if I go back, I'll go forward. The values of A and B, pause there for a second, and then I'll just combine these. All right, so sorry about that. I forgot a slide. So what we have is, like I said, this is the same formula that is at the top. So this is what we need to do next. We have to solve for the A's, the B's, and the C's before I just jumped for the answer, so I thought you might like to see how it's done. First things first is, remember this equation. The change of x over the change of y is equal to the tangent inverse of the azimuth, okay, or the tangent of the azimuth. Now, this is actually the point slope form of the equation of a line. So if I rearrange this equation and I leave the x's on tops and I move the y's to the other side. So it's y minus y1, and y1 is usually or y1 and x1 are going to be our first point normally, just to make our lives a little bit simpler. We can solve for the x, so we move the x over to the other side, so it becomes a plus x. Now, when we rearrange the equations to get all the unknowns to the left-hand side, we have x is equal to y tangent of the azimuth, 1 minus the y tangent azimuth, y times tangent, and y1 times the tangent of the azimuth plus x. All I did was multiply the factors out. Okay. Same thing for the second one. We have the x here, and we have if we move the knowns and unknowns on each side of the equation, you can see all I did was move the y over to the other side. So we want all the unknowns on the left-hand side of the equation. So we don't know what x1, left-hand side, not right. So these are the unknowns that I have on this side of the equation, y and x. That's what we're trying to solve for. We do know the x azimuth of the first line because it was given to us, but we don't know the x and y, and that's what we're trying to solve for, is the intersection of that point. So the first line says it's x plus the tangent minus tangent azimuth of 1 times y is equal to x1 minus y1 tangent of the azimuth. All of this is just rewriting the equations from the point slope form. All right. Now, by doing it this way, we can now take a look at, and all I did was move this down so you can still have it. In this equation, remember it's ax plus by equals c. Okay. So in this, a is the one in front of that x. There's nothing there, so it's an understood one. B is equal to minus tangent of a known azimuth. So here's my minus tangent of my azimuths, okay? And that's multiplied by the y, so that's where the B factor is. The C is the known x minus the known y tangent of the known azimuth. We know all of this. That becomes our constant. We can solve that instantaneously because we have the given values. So in this equation, x1, y1, 1,000 or 10,000, 10,000, and the azimuth of 50 degrees. So you can plug them into these. So now A becomes a value of 1, B is a negative 1.1918, and C is a value of negative 1,917.5359, blah, blah, blah. For the second line, we still have the same thing. So we got A, B, and C. In front of this one, A is the understood, minus tangent of 330 degrees is going to give us the B factor. And then the C factor is, again, we have the 20 and the 5,000, y and x and y. So we can solve out the constant C factor. So now we've got A's, B's, and C's solved for that we're going to plug back into our equation. So A1 is equal to 1, A2 is equal to 1. B1 is equal to negative 1.19, blah, blah, blah. B2 is equal to 0.57, blah, blah, blah. Okay, I'm not going to say all the numbers. You can visually see them. I'll say the first parts, but... Now the L is the constants. That's going to be your C1 and C2 from what you calculated for. The negative 1,917 and the 22,886. Okay, so C1 and C2. Now what we still don't know is going to be X intersection and Y intersection. This is what we're trying to solve for, these values here. So we're going to express the equation in a matrices form. So we're going to say A times X equals L. Now, we need to multiply both sides by the inversion, okay, the reciprocal of it. And the reason we're doing is we're trying to get rid of that. So, because we know when we multiply it together, it's going to give us an identity factor. So we have on this side, if we multiply the reciprocal on both sides, then we'll have only the identity matrix times X equals A sub the reciprocal or the inverse of A times L. Okay. Remember that remember that A multiplied by any matrix equals the original matrix. It's like saying 1 times whatever the value is. So that just drops out because X is what we're solving for, and X is going to be the X intersection value and the Y intersection value. So the known is going to be equal to the unknowns. All right. So first thing we have to do is find the inverse of A. So we have to do that same process that we did before, just to make sure that it's quote invertible. So here is our matrices: 1, negative 1.19, 1.57, blah blah blah. So the first step is the determinant. So 1 times that minus 1 times that. So that gives us minus makes it a positive, gives us 1.769, yada yada yada. Now we're going to find the cofactors. So we write down our matrix A, and row, column, positive number stays positive, okay? We've got the row, column, 1, but this is going to be negative because it's 1 and 2 making 3. Now we've got 1 and 2, again, negative becomes positive, and then 2 and 2, it becomes positive. When I say 1 and 1, 2 and 2, remember, when you're saying number of columns and number of rows. So number row 2, number row, or column row 2, number row 2 is 2 and 2 is 2 plus 2 is 4. So just keep in mind that. So now what we've got left is going to be our cofactor matrix. Okay, so all I did was take these numbers and now made it my cofactor matrix for A. Now we have to transpose it. All we did was flip. If you look down here, it's 0.57 and negative 1, 1.19 and positive 1. We flipped them, okay, rows to columns. Last but not least, we're going to take the determinant that we figured out the very first and divide each one by the determinant. And we'll come out with a new matrix that is the inverse of A. Okay, 1 over the matrix A is what we've got. Now, all we have to do is multiply. We're going to assume that it is an invertible matrix. What we have to do now is multiply to solve for the X. And remember, X is going to give us our X intersection value and our Y intersection value. So here's our inverted matrix. So I'm solving for X. Here's my inverted matrix. Here is my constants that we solved for C. And I'm going to multiply them. Negative 1,917 by 0.335 plus 22,886 times 0.673. That across, adding those across, is going to give me my X value. So 14,791.87 is the intersection of those two lines, and the Y value is going to be the negative 1,917 times negative 0.56, yada, 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 plus 22,886 times 0.565. Add those two together, and it's going to give me my Y intersection value of those points. So by using matrices, we can solve for our unknowns when we have two known points and the bearings of each of those lines to figure out where that intersection's crossed. Now, the inverse matrix functions, what I'll do in a different video is I'll show you how to do instead of doing all this by hand, I'll show you how to do it with Excel. But these are going to be your functions. M inverse, you're going to have M multi, which means to multiply. I'm assuming inverse you understand is the inverse matrix. Transpose allows you to transpose a matrix. And then here's a very important point is Control-Shift-Enter makes them work. But I'll do an Excel calculation spreadsheet with you on this to solve for it. But it's much simpler. You can do it in 2-3 seconds versus the step-by-step by hand, especially when you have more than a 2x2 matrix. All right. So that's the end of this video. Your next video is going to be on using Excel and the matrix calculations.